Hello everyone, and welcome to this session where we break down a fascinating physics problem. Today, we're going to dive into the mechanics of a car, specifically looking at how we can determine the torque produced by its engine. Understanding concepts like force, power, and efficiency is absolutely crucial in engineering and even in understanding the performance of everyday vehicles. Let's tackle our problem. A car of mass, 1,500 kilograms, is traveling at 45 kilometers per hour and accelerating at 2 meters per second squared. The engine RPM is 2,000. What is the torque at the crankcase if the drivetrain efficiency is 0.85? First, let's visualize this. Imagine a car on a road. We have its mass, its speed, and its acceleration. Inside the car, the engine is generating power, which then travels through the drivetrain. That's the gearbox, driveshaft, and differential to the wheels. There are some losses along the way due to efficiency. Our goal is to work backward from the car's motion to find the twisting force, or torque, at the engine's crankcase. Now, let's identify our key variables and constants. Mass, m, is 1,500 kilograms. This is the total mass of the car. Velocity v, 45 kilometers per hour. This is the car's instantaneous speed. We'll need to convert this to meters per second. Acceleration a, 2 meters per second squared. This tells us how quickly the car's velocity is changing. Engine RPM, n, 2,000 revolutions per minute. This is the rotational speed of the engine's crankshaft. We'll convert this to angular velocity in radians per second. Drivetrain efficiency equals 0.85. This means 85% of the power generated by the engine actually reaches the wheels. The other 15% is lost due to friction and other factors in the drivetrain. Our unknown is the torque, tau, at the crankcase. To solve this, we'll use a few fundamental physics principles and equations. Newton's second law. Force equals mass times acceleration. F equals ma. This will help us find the net force required to accelerate the car. Power, linear. Power equals force times velocity, P equals Fv. This will give us the power delivered to the wheels. Power, rotational. Power equals torque times angular velocity, P equals tau omega. This is how we'll relate the engine's power to its torque. Efficiency. Efficiency equals output power divided by input power, N equals P out over P in. This allows us to account for losses in the drivetrain. We'll also need conversion factors for velocity and rotational speed. Let's put these into action step by step. Step 1. Convert the car's velocity. Our velocity is 45 kilometers per hour. To convert this to meters per second, we multiply by 1,000 and divide by 3,600. Since there are 1,000 meters in a kilometer and 3,600 seconds in an hour. So, V equals 45 kilometers per hour times 1,000 meters over 1 kilometer times 1 hour over 3,600 seconds. This is the speed at which the car is moving. Step 2. Calculate the net force required to accelerate the car. Using Newton's second law, F equals m times a. F net equals 1,500 kilograms times 2 meters per second squared equals 3,000 newtons. This is the force that the engine must provide at the wheels to make the car accelerate as specified. For simplicity, we are considering only the force required for acceleration here, ignoring other forces like air resistance or rolling friction, as they are not provided in the problem. Step 3. Calculate the power delivered to the wheels. Using the linear power formula, P wheels equals F net times V. P wheels equals 3,000 newtons times 12.5 meters per second equals 37,500 watts. This is the useful power that is actually reaching the wheels to drive the car forward. Step 4. Calculate the power generated by the engine. Now we factor in the drivetrain efficiency. Since the drivetrain is only 85% efficient, the engine must produce more power than what reaches the wheels. We use E equals P out over P in, which means P in equals P out over E. P engine equals P wheels over E equals 37,500 watts over 0.85 equals approximately 44,117.65 watts. This is the total power the engine's crankshaft must generate. Step 5. Convert the engine RPM to angular velocity. The engine speed is given in revolutions per minute, but for our power equation, we need angular velocity in radians per second. 1 revolution is 2 pi radians, and there are 60 seconds in a minute. Omega equals 2000 RPM times 2 pi radians per revolution, divided by 60 seconds per minute, equals approximately 209.44 radians per second. Step 6. Calculate the torque at the crankcase. Finally, we use the rotational power formula. P engine equals tau times omega, rearranged to solve for torque. Tau equals P engine over omega. Tau equals 44,117.65 watts, divided by 60 second, equals approximately 210.65 Newton meters. This is the twisting force produced by the engine at its crankshaft. So, to summarize, the torque at the crankcase, given the car's acceleration and speed, is approximately 210.65 Newton meters. We can check our answer by verifying the units. Watts divided by radians per second correctly gives Newton meters. The magnitude of 210 Newton meters is also a very reasonable value for the torque output of a passenger car engine. This problem highlights how we can work backwards from observed motion and known efficiencies to determine the power and torque requirements of an engine. This understanding is fundamental in vehicle design, performance analysis, and even in optimizing fuel efficiency. A key takeaway from this problem is the interconnectedness of linear and rotational motion, linked through the concept of power and the crucial role of efficiency in real-world systems. This problem ties directly into topics like Newton's laws of motion, work and energy, and rotational dynamics, showing how different areas of physics combine to explain complex systems. Thank you for joining me for this problem-solving session. I hope this explanation has been clear and helpful. If you found this video useful, please give it a like, subscribe to the channel for more physics and math content, and feel free to share it with anyone who might benefit. Your comments and questions are always welcome below, and if you have a specific physics or mathematics problem you'd like to see me solve in a future video, consider supporting the channel through a donation. Each month, I'll select a few viewer-submitted problems to tackle in their own dedicated video. See you next time.